In this video, we're going to go over how to do mass-to-mass stoichiometry examples here. So just as a quick refresher, the 4 steps to any stoichiometry calculation is to first create a balanced chemical reaction. Step 2, find your moles of your given substance. Step 3, use your mole ratio to convert the moles of your given substance to the moles of your unknown substance. And then we'll have to add in step 4 over here. Step 4 is simply just answer the question, which typically that involves converting moles of your unknown substance into whatever units the question's asking for. Okay, so we'll highlight that just because it's important. But let's go on to our first example here. So we're asked what mass of zinc sulfide is required to burn in the presence of 45 grams of oxygen. So how you know it's a mass-to-mass stoich question is because they're asking for mass and they give you a mass. Okay, so let's start off with our balanced chemical equation. So because it says the word burn here, that's my indicator that we have a combustion reaction happening. Okay, and it says that zinc sulfide is burning in the presence of oxygen. So those are our 2 reactants. So we have zinc sulfide reacting with oxygen gas. Now with zinc, let's see what charge it likes to have. So zinc likes to have a charge of +2. And then sulfur, which is right here. So sulfur, because it's part of group 16 here, that's why it likes to have a -2 charge. So this is +2 -2. 2 minus 2, it's equal to 0, so this compound is already balanced. Now, since there isn't the mention of any solutions, and since this is an ionic compound because you have a metal and a non-metal bonded together, we can assume that this is going to start off as a solid here. Now for predicting our products, for combustion reactions, you kind of got to imagine that oxygen just reacts with each element individually in your compound here, okay, and creates the most common oxide with that element. Okay, so the first one I'm going to do is zinc oxide. Okay, so since zinc likes to have a 2+ charge here, and oxygen likes to have a -2 charge, the compound we've created, it's already balanced. And since it is an ionic compound, we can assume that it is a solid. Okay, so remember, when oxygen reacts with metals, you're going to go with the most common charge. And for zinc, there's only one possible charge. It's not a multivalent metal. So that's why I knew that the oxide that oxygen would form with zinc would be this compound, just with balancing the charges there. All right. Last but not least, we got to react oxygen with sulfur, and the most common oxide that's created with sulfur is going to be sulfur dioxide, which is a gas. Okay, so as a reminder for the most common oxides that can get formed with certain elements, make sure to review those back in your notes that talk about combustion reactions. So we got our skeleton equation so far. Let's make sure that it's balanced here. So we got 1 zinc going in, 1 zinc coming out, so that's balanced. We got 1 sulfur going in, one coming out, that's balanced. But we have 2 oxygens going in and 3 oxygens in total coming out, because we have 1 from here and then 2 from sulfur dioxide. Okay, so sometimes with this, you got to do a little bit of trial and error. So let's just see how this works out. So my guess is, what if I increase this to 2 so that we have a total of 4 oxygens going into our reaction? And then what if I also increase this to 2? So this 2 doesn't just affect the zinc, it also affects the oxygen. So we have 2 oxygens coming from here plus the 2 coming from sulfur dioxide. So that equals 4. So our oxygens, they are balanced out. Now let's just double check the other elements. So zinc, there's 2 of them coming from zinc oxide, and we only have 1 here. So let's put a 2 in front. Okay, so our zincs are balanced, our oxygens are balanced. Now let's check out our sulfurs. So we got 2 sulfurs going in and only 1 coming out. So if I put a 2 right here, that's going to cause the oxygens to become unbalanced now. Okay, so now everything except for oxygen is balanced. Okay, so let's go back to oxygen. So right now we have 2 oxygens from here, and then 2 times 2, so 4 oxygens coming from here. Okay, which is 6, which is good because that's a number we can easily get to here. Okay, so if we go, 2 times 3, that's 6. Okay, so oxygen's balanced. We got 6 going in, 6 coming out. For zinc, we got 2 coming in, 2 coming out. And for sulfur, we have 2 coming in, 2 going out. Everything's balanced. All right. So that was step number 1. Step number 2, actually before step number 2, we're just going to organize our information first. Okay, so we're told we got 45 grams of oxygen. So let's write that here. And whenever we have the mass for something, or we're asking for the mass of some chemical species, we're always going to want to make sure that we write out what the molar mass is and just get that out of the way. Okay, so if I look at oxygen, the molar mass for 1 atom of oxygen is 16. So since we have 2 here, 2 times 16, that's going to be 32. Okay, so I would say the most common mistake with combustion reactions is forgetting that oxygen is diatomic. So watch out for that. All right, and we're asked what mass of zinc sulfide. So mass, we got no clue. Molar mass, we need to figure that out for zinc sulfide. Okay, so going to our periodic table, so zinc, that's 65.41. And there's only 1 of it, so I'm not multiplying it by anything. And then sulfur, let's check that out. I think it's 32.07. Yep. Okay, so if we add those together, we're going to get 97.48 grams per mole. Alrighty. So let's start off with our given substance, and in step number 2, we're going to figure out, okay, how many moles of this given substance, or how many moles of oxygen, do we have? So when I say given substance, I mean the substance that you're given the most information for. Okay, so as a quick reminder for our formula, mass is equal to moles times molar mass. We want to rearrange this to isolate for moles. So if I look, molar mass is multiplying moles. So the opposite of multiplying is dividing. So I got to divide both sides by molar mass. Those cancel out. And we're going to get mass divided by molar mass is equal to moles. So that is going to be the formula that I'm using here. Okay, so moles is equal to, so our mass of oxygen is 45 grams, divided by our molar mass of oxygen is going to be 32 grams per mole. So remember that the mass and the molar mass that you use have to belong to the same substance. Okay, so 45 divided by 32, let's do that. So that's going to give us 1.40625. So that's moles of oxygen. Okay, so step number 3 now. So we finished step number 2, on to step number 3. We use our mole ratio to convert this from moles of given to moles of wanted. So we're converting from moles of oxygen to moles of zinc sulfide. So let's just use a different color to show that it's a different step. So times by fraction sign. So what we want is zinc sulfide. What we're given is oxygen. So the coefficients in front of both of those are 2 and then 3. So the mole ratio, this is why you need a balanced chemical equation so that you can actually write out your mole ratio. Okay, another thing I want you to pay attention to is when I was calculating my molar mass, I did not take the coefficient into account. I just counted it for 2 atoms of oxygen because the 2 came from the subscript. But I did not worry about the coefficient when I was figuring out the molar mass, because I knew I was going to take the coefficient into account in the mole ratio. Okay, so just as something to watch out for, because sometimes students do that. When you're figuring out the molar mass, do not take into consideration the coefficient. Okay? But you do need to take into account the subscript numbers when you're figuring out molar mass. Okay, so 1.4062 goes on, times by 2, divided by 3. That's going to be 0.9375. And this is now going to be moles of zinc sulfide. All right, so now that we have our moles of our wanted, now we're on to step 4, which is answer the question. Okay, so the question asks us, what mass of zinc sulfide do we have, or is required? So we need to go from moles and convert that into mass using our molar mass. Okay, so as a reminder here, the formula I'm using is mass is equal to moles times molar mass. So the moles of zinc sulfide times by the molar mass of zinc sulfide. So once again, these have to belong to the same substance. So molar mass of zinc sulfide, that's at 97.48 grams per mole. Actually, I'll write that a little differently. Grams per mole. All right, so moles are going to cancel out. And when we multiply those together, we're going to get 91.3875. So as always, we're going to take sig digs into account. So it looks like here we were given 2 significant digits. So that's what my final answer needs to be in. Okay, so I start counting from the left, 1, 2, there's my cutoff line. So we will need 98 grams of zinc sulfide. Alrighty, we're going to go on to the next example here, and I'm just going to give you some options just in case you weren't a huge fan of using the formulas here. I'll give you some options and you can choose which way you want to tackle these problems. So the question is, what mass of oxygen is required when 5.2 kilograms of methanol, CH3OH, is burned? Okay, so once again, that keyword burned, that tells us this is going to be a combustion reaction. So let's do this. And since methanol is a hydrocarbon fuel, that just means we're going to get carbon dioxide and water vapor as products. Okay, so how I figured out that the state for methanol was liquid is because it tells me that right here. Now, if you were given the name of methanol but not given the formula, where you could look that up would be on page 4 and 5 of your data booklet. Okay, so for methanol here, we could find that. There's methane, there's methanol, right there. Okay, so if you're ever given a name of a hydrocarbon and you're not sure what the formula is, sometimes you can look it up on page 4 and 5 of your data booklet. Okay, so as I said, because this is a hydrocarbon, we're going to be getting carbon dioxide and water vapor as products. So we got our skeleton equation here. So what we need to do is we need to balance it. So for carbons, one going in, one coming out. Okay. For hydrogens, by the way you balance reactions like this or combustion reactions is it's always going to be carbon first, hydrogen second, oxygen is always balanced last. That's the easiest way to balance these. Okay, so for hydrogen, we have 4 coming from methanol, and we've got 2 in our product. So I'm going to put a 2 right here so that those are balanced. For oxygen, we have 3 on our reactant side, and we have 2 plus, and we have 2 coming here, so we got 4 on our product side. Okay, so what we need to do to make our lives easy here is, since there's only a difference of 1 between the amount of oxygens on the reactant side and the product side, I want to increase methanol just by 1. Okay, so I'm increasing the coefficient from 1 to 2 on methanol here. So that's going to cause us to have 4 oxygens on our reactant side, 4 on our product side. So the oxygens are balanced, but that's going to throw everything else out of balance as well here. Okay, so we're going to start back at carbon. So we got 2 carbons coming in. Now we need 2 carbons coming out. Okay, so carbons are balanced now. I do know that that's going to throw oxygens out of balance once again, but that's okay. Let's just keep on going the way we were going. So we did have 4 times 2 hydrogens, so that's going to be 8 hydrogens, and right now we have 4 hydrogens on the product side. Okay, so let's erase this. I'm going to increase this to 4. Okay, so now we have 8 hydrogens on the product side as well. And let's see what happened to our oxygens. So for oxygens, we have 2 coming from methanol, and then 2 coming from the oxygen. So we got 4 oxygens on the reactant side, and we have 2 times 2. So we got 4 plus 4 times 1. It's going to be 4. So we have 8 coming from the product side. Okay, so 4 versus 8 here. I'm thinking to myself, oh, okay, we just need to have 4 more oxygens on the reactant side. So how we're going to achieve that there is I'm going to be focusing on increasing the amount of oxygen gas we have, since the difference is an even number. Okay, so what I'm going to do is I'm going to increase this to a coefficient of 3, and the reason being is because then I will have 6 oxygens coming from here, plus we still have the 2 coming from methanol, so 2 plus 6, that's 8, and now everything's balanced out. All right, so let's organize our information. So we got 5.2 kilograms. Okay, which I'm going to convert into grams here. So as a quick reminder of the metric conversion line, it looks something like this. So I'll write it out and then I'll show you how I memorize it. Okay, so how I memorize this is I've just created a sentence that starts with each of the letters of the prefixes. Okay, so just as another quick reminder, this prefix is tera, giga, mega, kilo, hecta, deca. Base units are any units where the symbol for it is just made up of usually one letter. So like meters, the symbol for it's just M. Liters, it's just L. Right, so on and so forth. The exception for chemistry being moles, that's one of your base unit, but another way you could think about it is base unit is just a unit that doesn't have a prefix in it. Okay, this prefix is deci, centi, milli, micro, nano, and then pico. All right, so converting kilograms into grams, that means we're starting at kilograms and then grams as a base unit. So I count 1, 2, 3. So we need to move the decimal over 3 to the left. So if I go, let's change the color, 1, 2, 3. Then this is going to be, we're just going to fill in these spots with zeros. So 5,200 grams. For molar mass, we're just going to add up each element individually here. So we got carbon, 12.01. Then we have hydrogen, but there's 4 of them. Since hydrogen has a molar mass of 1.01, and there's 4 of them, I'm going to go, okay, well, 4 times 1.01, that's just 4.04. Okay, so I'm getting 4 hydrogens because there's 3 here and then there's 1 more right here. And then oxygen, there's just 1 of them, and oxygen has a molar mass of 16. So if we added all of that up, we're going to get 32.05 grams per mole. Okay. And then we're looking for what mass of oxygen. So mass of oxygen, we got no clue. And the molar mass, so oxygen, the molar mass of just 1 atom of oxygen is 16. If you look it up on your periodic table, you can see that it's right here. But we have 2 of them because of that subscript, so 16 times 2 is going to be 32. All right. So as promised, I said I would show you a slightly different way to do these questions. It's going to still be the same exact process. However, we're just not going to write out the formulas. So if you like formulas, absolutely you can stick with the method that we have been using. However, if you wanted to give this a try, go for it. All right, so we're still going to start with find moles of your given. Okay, so what I'm going to do is I'm going to take this 5,200 grams and I'm going to say to myself, okay, I know I want to cancel out grams and be left with moles. Okay, so if grams is on the top, according to unit analysis, if I put grams on the bottom, since I have the same exact units in the top and the bottom, they will cancel out. And I want to be left with moles in the numerator, so I'm going to put that up top. Okay, now what do I know with the units that have like grams and moles in the units? Well, that's going to be molar mass. Okay, so the number goes wherever the grams go for the units for molar mass. Okay, so I'm going to put 32.05. So grams cancels out, and moles is, if it really bugs you not to have a number there, remember that molar mass is grams per 1 mole of substance. So if you want to, you can put the 1 there. Okay, but ultimately what we're doing is we're taking 5,200, timesing it by 1 and then dividing it by 32.05. Or, if you think about it, 52 times by 1, that's still going to be the same number. So essentially, we're just taking 5,200, dividing it by 32.05. So that's going to give us, let's write this out, 5,200 divide by 32.05. If you want to write the times by 1 and then divide by 32.05, you can, but this will get you the same answer. So we got 162.2464, goes on forever. And this is our moles of methanol. Step 3, use your mole ratio to convert moles of given into moles of your unknown or your wanted substance. Okay, so I'm going to have to squish this in a little bit, if that's okay. All right, so our given substance, CH3OH. Our wanted substance is oxygen. What are the coefficients for those? Well, 2 for methanol, 3 for oxygen. Okay, so we're taking our number, timesing it by 3, dividing it by 2. So we get 243.3697, goes on forever. And that's moles of oxygen. Now, Step 4, give the question what it wants. Okay, so the question wants the mass of oxygen. Okay, so mass is usually in grams, so I know that I need to convert from moles into grams. So I'm going to go, okay, times by a fraction sign. So in this method where you're using unit analysis, you always take your given number and then go times by a fraction sign. Okay, and then you work on figuring out, okay, how do we cancel out the units? So we know we want to cancel out moles and then be left with grams. So moles is on the top. I'm going to put it in the bottom to cancel it out. I want to be left with grams in the numerator, so I'm going to put it up top. So moles cancels out. Okay, I'm going to erase this so that it's easier to see. All right, so what do we know that has the units grams per mole? Well, that's molar mass. Okay, so I'm going to be looking for the molar mass of oxygen because we want to multiply it with the moles of oxygen. So it has to belong to the same substance just like before. So I got to multiply it by 32, and the 32 is going to go where the grams goes. All right, so times by 32 is equal to 7,787.8315 goes on. And that is grams. And we need to take into account sig digs here, which looks like we're only given 2 sig digs. So that's what we're going to be working with, 2 sig digs. So I start from the far left, counting my significant digits. So 1, 2, so there's my cutoff line. So since my cutoff line comes before the decimal, that's how I know I'm going to have to use scientific notation. Okay, so let's see. Scientific notation, the goal of it is to only have one non-zero digit in front of the decimal. So I'm going to move my decimal to make that happen. So 1, 2, 3. So I got 7 point, and then I'm going to round up that 7 that's in front of the cutoff line. And then times by 10. Okay, so for the exponent, we got to show how many, or we got to use the exponent to represent how many spots we moved the decimal place. So we moved it 3, and since our original number, 7,787, is above 1, that exponent is going to be positive. The only time the exponent's negative is if your original number, before you put it into scientific notation, is between 1 and 0. Okay, so this is going to be grams of oxygen. So another way you could represent this, because there's 1,000 grams in a kilogram, you could also represent this as kilograms here. So if you divide this by 1,000 to get into kilograms, it's just going to be 78 kilograms of oxygen. So both answers are acceptable because the question didn't specify what units it wanted mass in. So either or is good. So one thing that I just want to talk about before we end this video here is, even though it looked different, like our process looked different compared to what we've done before, it's still the exact same process. Okay, so notice in the first step, in the first example, we took mass and divided it by molar mass. Okay, so what did we do in our first step over here? We took our mass and we still divided it by molar mass. Okay, for the next step, we, like in our original example here, we took the moles and we multiplied it by the mole ratio, which we still did here. We took our moles of methanol and we multiplied it by our mole ratio. Okay, and then in the last step, we took our moles of our wanted substance and multiplied it by the molar mass of our wanted substance, right? Which is what we did here. So we took our moles of our wanted substance, we multiplied it by the molar mass of that wanted substance. Okay, so even though this process looked different than what we did up here, both still get you to where you need to go. It's your choice whether you want to use formulas or if you want to use unit analysis to solve stoichiometry questions, then you're welcome to do so.